All right. A few more things that I want to say about this idea of cardinality, and then this will be our last, I think my last comments on this subject for now anyways. Is so in the previous videos we proved that if we take the union or the Cartesian product of two countable sets, you get a countable set. And a little bit more is true. If, say you have a whole collection of, say you have a whole collection of countable sets, and I want to be very careful when I say this. Say you have a countable collection of countable sets. In other words, suppose you have a collection, say A1, A2, and so on, are all countable sets. When I say and so on, what I mean is have infinitely many, that's fine, are countable sets. Then one is that any finite union of countable sets is countable. So A1 union, A2 union, all the way out to AN, that's going to be countable. And it's going to be countable for all n greater than or equal to 1. And that proof is really just the fact that the union of two countable sets is countable plus induction. And I'll let you worry about that, how to write that out formally. Likewise, the Cartesian product, A1 cross A2 cross, say, AN, is going to be countable. So that's also going to be countable for all n greater than or equal to 1. And surprisingly, you can actually take the union of however many sets you want. That'll be countable. A1 union A2 union however much you want is also countable. So let me write this a little bit better as to what I'm saying. The union of these sets, I don't know why I said union, funny like that. The union, A sub I, as I goes from 1 to infinity, is also countable. Now, the proof for number 3 is substantially different. So the proof for number 3 is substantially different than the proof for number 1. I will let you think about how to do number 3. I would never ask how to. I would never ask you to prove item number 3. Items 1 and 2 are straightforward, and I just talked about those. But it turns out that the union, the countable union of countable sets, is countable. Pithy, I know. But that's all that there is to say. So just as a warning, the countable Cartesian, the infinite Cartesian product of countable sets is not countable. In fact, this is slightly strange, but if you were to take the Cartesian product of an infinite number of sets, that Cartesian product can be uncountable even if the sets that you're taking are finite. So let's say we need to define this a little bit, but let's say that if A1, A2, A3, and so on, let's say it this way. If, let's say we have A sub I, where I is some non-negative integer, so this means that you have a countable collection of sets. Is a countable collection of sets. Then the Cartesian product of all of those sets, and I need to think about how I want to write this, then I'll just write it out in words because I think that'll be the least confusing, but then the Cartesian product of all of these sets could be uncountable. In fact, it will be uncountable, even if the sets A sub I are finite for all I. Okay, and so there's something substantially different about the infinite Cartesian product of a bunch of sets that makes it possible for it to be uncountable. The way that I would like for you to make sense of this is think about each of these sets. So consider each set A sub I to be the set 0 through 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what is the Cartesian product? Well, what you're doing is if you were to look at the infinite Cartesian product of this set with itself infinitely many times, you're looking at the set of ordered sequences, basically, from 0 to 9. And what you can do is you can put those in one-to-one correspondence with a set of real numbers. So you can think of an element of this Cartesian product as being identified with a real number, and it's the real number you can even make it identified with a real number that's between 0 and 1, that's fine. But it's the real number that has, so here's what I mean. So for example, if you were to look at A1 cross A2 cross A3 cross A4 cross A5 and so on. Now these sets are all the same. So that means that you're going to look at ordered tuples where each value can be from the integers from 0 to 9. So this includes things like you could have, for example, say 4, 7, 9, 2, 3, 5, right? That's something that would be in that set, that Cartesian product. But what you could do is you could put this in one-to-one correspondence with the decimal point 4799235. And notice that if you think about all the real numbers, those are really just you're writing sequences of the digits 0 through 9, and they're infinitely long. And you can put that in one-to-one correspondence with these tuples, right? You can put the first decimal in the first spot, second decimal in the second spot, and so on. And so if the set of real numbers is uncountable, then the set of all those tuples has to be uncountable. And therefore, this Cartesian product has to be uncountable, even though these sets are finite. It's a little strange, but it turns out that when you take the Cartesian product of infinitely many sets, that will be uncountable, even if the sets that you start with are finite. Okay? That's in stark contrast to what happens with unions. A countable union, meaning if you take the union of infinitely many sets, that's going to be countable as long as each of the sets is countable. Okay, so if these sets are finite or countable, then this union will be countable. Okay, so that's the first thing that I wanted to say there. The second thing, and this is where I want to end, I think this is the last thing to say about cardinality in general. But I want to just mention two really deep theorems here. So the first one is called, I need to make sure that I can spell this mathematician's name correctly. Sorry, I should have studied. But it's the Schroder-Bernstein Theorem. So let me make sure that I can spell that name correctly. Schroder, S-C-H-R-O-D-E-R, Schroder-Bernstein. Okay, B-E-R-N-S-T, yeah. So the Schroder-Bernstein theorem says that if there exists, and this is an obvious sounding theorem, but it turns out to be incredibly intricate and really, really tricky. So tricky that people's names are attached to it. So in math, oftentimes, if there's something that's kind of obvious, then often your name's not attached to it. But if the name's attached to it, that means it's probably pretty deep and pretty hard to prove. So the Schroder-Bernstein theorem says that if there's a one-to-one function, so if there are one-to-one functions say F1 from A to B, and F2 from B to A, then there's a bijection. So then there exists a bijection F from A to B. Now, this is an obvious fact when A and B are finite sets, because we know what that means about their cardinalities, and these are just numbers, so we can say that A and B must have the same number of elements, and therefore there's a bijection between them. When A and B are infinite sets, this is an incredibly tricky, intricate thing to prove. Okay, so I'll just leave that as a statement there. The last thing that I'll just leave as a statement is called Cantor's theorem. And I have the proof written up in the notes if anyone wants to see it. But Cantor's theorem says that there is no bijection, there can be no bijection between a set A and its power set. So it doesn't matter what the set is, and this actually gives you a way that you can define infinitely many infinities, but there's no bijection between a set and its power set. So if A is a finite set, then you know that there can't be a bijection from a set to its power set, because let's say A has n elements in it, then 2 to the A has 2 to the n elements in it, and it's always the case, you can prove this by induction, that n is always less than 2 to the n for all n greater than or equal to 0. Okay, that's always the case. 2 to the n is always larger than n. So there can be no bijection when A is finite. When A is infinite, this is a little trickier to prove, but I have the write-up written in the notes. But when A is infinite, it turns out that there's also no bijection there. It turns out that the power set is strictly larger than the set itself. What that means is that if you wanted to build infinitely many infinities, what you can do is start with the non-negative integers. Think about, so that's your A. Think about the power set of the non-negative integers. That's 2 to the A. And that must have a cardinality larger than the integers themselves. And in fact, if you look at the power set of the non-negative integers, where A is, so if A is the non-negative integers, then the power set actually can be put into one-to-one correspondence with the reals. It's an uncountable set. But then you can keep going. If you take the reals, and then you look at the power set of the reals, that must have a cardinality that's strictly bigger. So there's actually a bigger infinity than uncountable. And whatever the power set of the reals is, if you take the power set of that, you get an even bigger infinity, and you can do this infinitely many times. So it turns out that there's actually infinitely many infinities. In fact, there's uncountably many infinities that we can have. Okay, so I think that's the last I wanted to say about cardinality.